My thesis title is a deep regression model for simulating force plate using smart insoles. In biomechanics laboratories, force plates are considered the most important tools for capturing these intricate dynamics because they provide researchers and clinicians with a means of analyzing movement patterns, analyzing muscle activation, analyzing joint motion, and assessing body mechanics in diverse environments. Through the use of this tool, the identification of abnormal movement patterns, the assessment of balance, as well as the development of evidence-based, customized treatment protocols for physical therapy and sports medicine have been successful. Force plates have played a pivotal role in providing insight into how forces are exerted upon a body when it is moving or at rest. These tools have traditionally been used within the confines of laboratory settings. Smart insoles can be used to simulate force plate measurements in order to overcome this limitation. In addition to replicating force plate functions, smart insoles extend biomechanical analysis to a variety of settings and activities. It is possible to capture and analyze data in real time using these wearable devices during routine activities, sports, and rehabilitative exercises under realistic conditions. Based on existing mobile force plate, the methodologies depended heavily on Higuchi's algorithm, lack the ability to perform nonlinear transformations and predict outcomes for unseen data. There is a limited diversity in the movement scenarios. They are using R-squared score to evaluate the model. ResNet regression model, which are capable of handling nonlinear transformations and predicting on unseen data. To evaluating the accuracy of predictions in relation to the actual data, the using R-squared and RMSE value would be more appropriate. By increasing movement scenario, this can make more comprehensive and that can accurately analyze a wider range of human movement patterns. Contributes to biomechanics by enhancing smart insoles as mobile force plates. A ResNet regression model is created to overcome traditional method limitations, enabling robust handling of complex variables and accurate predictions for unseen data. Both R2 score and RMSE are used for a comprehensive evaluation of model accuracy, ensuring predictive and precise results. Furthermore, by incorporating a standing pattern in force plate simulations, our model can analyze a broader range of human movements, enhancing balance and postural stability assessments. This significantly broadens smart insoles applicability in both clinical and sports settings. Regression analysis is a technique used to predict a target variable based on one or more predictor variables. It can be used for forecasting and finding relationships between variables. ResNet, a type of convolutional neural network traditionally used for image classification, can be adapted to perform regression problem. This adaptation requires a few changes. For instance, the last activation layer needs to be changed to a linear function since softmax, which is typically used for classification, isn't suitable for regression tasks. In addition, the loss function must be modified to something more appropriate for regression, such as mean squared error, MSE. These adjustments allow the ResNet architecture to effectively handle regression problems. The model initiates with an input layer specifically designed to process smart insole data. This data, generally pre-processed into fixed-size windows, aligns with the input layer format. In this case, the input size is set to 89:1 to accommodate the features provided by the smart insole data. Following the input layer, the model deploys one-dimensional, 1D, convolutional layers that apply 1D filters to discern patterns across the time series, such as the rhythm of steps or shifts in pressure distribution. The model likely consists of one or more residual blocks, each containing a few 1D convolutional layers and a shortcut that connects the block's input and output. This design enables the model to learn when to make use of or bypass the layers in the block. Each convolutional layer is succeeded by an activation function that infuses nonlinearity, thus enabling the model to learn complex patterns. Additionally, batch normalization can be implemented to stabilize the learning process, augment training speed, and mitigate the risk of overfitting. After traversing all the residual blocks, the feature maps are handled by a global average pooling layer, which reduces their dimensionality, preparing them for the final stages of the network. A fully connected or dense layer is then applied, transforming the pooled features into a single vector of values and learning to emphasize the features that are most critical for predicting the outcome. Ultimately, we reach the output layer, which, in this case, consists of 6 neurons with linear activation functions. Each of these neurons predicts a specific force plate value, Fx, Fy, Fz, my, Mx, Mz. These continuous values, generated based on the input received from the dense layer, represent the model's predictions for the 6 force plate values. The reason standing data is more difficult to be modeled than walking data. The hypothesis is that the changes in standing are much less obvious than walking. Therefore, the low-cost sensors used in the smart insole might not be able to capture such subtle changes, which caused the inconsistency in matching smart insole data and force plate data. Solution treats such inconsistency as noise in the data, and use noisy label techniques to remove such inconsistency from the data group the data based on their similarity and create one model for each group. To effectively remove noise from our data, first we train the ResNet model using the original data and then utilize this model to generate predictions. Once we have these predictions, we evaluate the results based on the loss performance, which in this case, is quantified using the root mean squared error, RMSE. The data are then sorted from low to high according to their RMSE values. We interpret higher RMSE values as an indication of noise data since these values signify a greater discrepancy between the predicted and actual values. Based on this interpretation, we then remove the data points associated with high RMSE values, applying the best parameters for this process. This method allows us to minimize the impact of noise on our model, thereby improving its accuracy and reliability. In conducting time series analysis, we are faced with constraints in our computing environment due to limited memory capacity. Given this issue, the time series data from 21 participants can't be processed efficiently. Consequently, we need to resort to data downsampling to circumvent the problem. Our smart insole and force plate data, which initially have a sampling rate of 50 data points per second, will be downsampled to a rate of 5 data points per second. This downsampling is essentially a form of data compression that reduces the memory requirement for our time series analysis without a significant loss in the quality of the data. Following the data downsampling process, we perform a time series analysis using various metrics. The results derived from this analysis are subsequently used for data clustering. We apply a clustering algorithm which automatically determines the number of clusters based on the time series analysis results. This process begins by randomly selecting a data point as the initial centroid. Following this, each participant is assigned to the nearest centroid, typically based on a measure of distance. The centroid of each cluster is then recalculated as the mean of all sequences in that cluster. This step is iteratively repeated until the centroids are stable, signifying that the algorithm has successfully grouped the participants. The result is k clusters of individuals with similar standing patterns. For each cluster, a custom model is created, enhancing the accuracy of simulating force plate measurements and thereby improving the effectiveness of smart insoles in diverse real-world scenarios. The following is an example of the results of grouping data based on similarity using DTW metrics. Using the dynamic time warping (DTW) metric, we implement k-means clustering on our dataset to group data based on standing pattern similarities. The number of clusters is determined automatically through DTW. The process begins with a randomly chosen data point as the initial centroid, and each individual is then assigned to the nearest centroid based on DTW distance. Centroids are recalculated as the average of sequences in their cluster and the process repeats until centroids stabilize. This results in k groups of individuals, each sharing a similar standing pattern. Here the results of Fx from walking predictions. From ground truth the model have good predictions. The following are our results from predicting Fx values. It appears that the model for standing patterns is not yielding results as favorable as the model for walking patterns. At present, we are still conducting investigations to understand and improve the performance of the standing model.